Hello everyone, I'm Pratap here. I welcome all of you who are preparing for 2026 CS2 April May examinations. Let me start with some exam questions, old exam questions. This will help you to develop the concept. You might not get this kind of a question once again. These are very easy. Anyway, let me show you some questions. Now, this is Institute and Faculty of Actuaries question. So it says explain why each of the following matrices is or is not a valid transition matrix for a Markov chain. This is the question. Okay. If you see here, the probabilities are given 0, 0, 0.5, 0.5. This is the transition matrix. So you can write like this 1, 2, 1, 2 here. That means if you draw a graph, it will look something like this. If you draw a graph here, okay, let me draw like this. If you draw a graph here, here you have a state 1, here state 2. You consider any 2 points, t to t plus 1, t could be 10, it could be 1 also. Suppose this is 10 and 11, this is 1, this is 2. So this matrix is given. So from 1 to 1, 0, I mean there is no way. From 1 to 2, it's 0. The total probabilities must be equal to 1. So this total probability is not 1. So, I mean, there is a problem. So this is not. The question is, you need to decide whether this is valid or not. This is the question. Now, consider the second transition matrix. You add all these three. 1, 2, 1, 2, 3. If you add all these three, 0 0.5, 0 0.3, 0 0.2. The total is 1 here. How about this? From 2, you can go to 1, 2, 3. So again 0 0.3, 0 0.1, that is 0 0.4 plus 0 0.6, that is 1. Again 1. Okay, that's fine. However, you remember, in case of a stochastic process, when you define 3 states here, 1, 2, 3, you need to define how many? 2 are here, 1 and 2. How about this? 1, 2, 3. This is not possible. Suppose this is any on timeline, any point. It could be 8, 9. So what will happen is you have 2 states here, you have 3 states here. That's not possible. It should be a square matrix. It's not a square matrix. So either you write another row here, or you need to delete a column here. Again, this is not. How about this? 0.5, 0.5, that's 1. 0.2, 0.8, 1. 0.6, 1. 3, 3, it's a square matrix. The number of rows and the number of columns, they're equal. So there won't be any problem, right? So this is yes. How about this? 0.5, 0.3, yeah, that's 1. However, there is a negative number. Okay. Remember, we'll go to generator matrix later. However, we're talking about a stochastic process here. That means all are probabilities. All are probabilities. The probability can never be a negative number. That is the reason it will not satisfy. That means it will not be a transition matrix valid. Okay, the question is whether it's valid or not. It's not valid. That's all. Done. How about this? This. A Markov chain has the following transition matrix given. Already it is, because it's a question. So the question is draw a transition graph for this Markov chain, including the transition rates. This is the question. And the second one is explain whether the Markov chain is irreducible and periodic or aperiodic, whatever. Our subject is here in today's class, aperiodicity and irreducible. So we'll say like this. We'll see whether a Markov chain is irreducible or not. Okay, this is one important thing you didn't learn or you didn't understand before. You'll understand today for sure. But remember, the subject is not reducibility. The subject is irreducibility. Because irreducibility is what we are interested in today's class. in today's concept, whatever we will develop today. And what about the second one? Aperiodicity. Okay, that's very important. Again, that's a straight concept. We'll go to that. And I'll come back to this one. Okay, before that, let me do this. ABC, I can write ABC here. Transition graph. Here you write A, then B here, C here. Now, A to A, I mean, there is no way you can go. There is no self loop here. A to B, yes. 0.6 probability. How about A to C? Yes, 0.4. And total is 1. That means what will happen? After one time period, again, time and again I'm repeating, because you need to develop the fundamental now. Otherwise, what will happen when you go to Kolmogorov's forward differential equation and continuous time stochastic process or backward differential equation, there you will have a lot of doubts. Anyway, I'm talking about two time points. It could be 2021 or 1, 2, doesn't matter. We are talking about homogeneous ABC here, ABC here. So that way, this is our stochastic process diagram. These are the states. We write only states here, and the transition probabilities we write. So A to A is not there, but yeah, next time what will happen? Anyone in A, either that guy will go to B or C next time. I mean, this is not there. That means there is no self loop here. This is absent. Zero probability. Anyway, that's not required. Then how about B? From B to B, there is no way. B to A 75. Yes, we'll write 0.75. How about B to C 0.25? Yes, total is 1. And this carries 2 marks. Then C to C not there. C to B 0.5. C to B 0.5. How about C to A 0. C to A 0.5? Okay, so we can draw something like this 0.5. So this carries 2 marks. Good, right? Now the second one is irreducible. Remember, here I am explaining irreducible means you can go from each state, because we'll not get a lot of time. We need to spend most of our time in solving the exam questions. Okay. So each state, from each state, you must have a path to any other state. This is the definition. Irreducible. Each state, you start from A. Can you go from A to B and C? Yes, you can go from A to B, A to C. That's fine. A to B, A to C. How about B? You check from B. Can you go from B to A and C? Yes. Can you go from C to A and B? Yes. Okay. This one I will discuss. Okay. Because I will start with this one. I explained. I'll come back to this. Now, what about this? Okay. This is a question. Andy, Brenda, and Carol. These are the 3. So the question here is, define a Markov chain. You need to define first of all. Then the manager of a sales team keeps record of how much each of the 3 sales staff. Okay, these are the 3 sells each week. That is the question. Okay. So the data is given 0.4, 0.3. I mean, if you start with Andy this week, here also let me write A, B, C, here also A, B, C. Ultimately, you need to write 1, 2, 3. The probabilities are given. The question is, so here it's given already. Okay, this is given. You are here, they are saying. Okay, this week. Calculate the probability that each member of the sales staff makes the most in the 3rd week of April. Okay, so this is given first week. Remember, this is a stochastic process where we have weekly data. Okay, this is stochastic process where you observe the stochastic process each week. Okay, because coming to stock price, you can observe each day, you can observe each hour, you can observe each second, each moment also. Okay, so the time you can take continuous also. We are not doing that. That will come later, but here every week. So you can start with 0, 1 by 7, 2 by 7, that way. Okay, weekly. So here you know that Brenda is the winner now. Okay, Brenda is the winner now. Now the question, winner in the sense, uh, it says most. Okay, that way it's winner. Okay, you are able to sell more. Anyway, what about this? So here who will be? And again, you will know how to estimate this, but now estimated values are given. So this is first week, 0 means first week. Okay, you can write first of month, then this is 7th, this is 14th, after 2 weeks. So if you want to find here to here, then there is a direct probability. B to B, B to B 0.5, this is given, B to B 0.5, this is given. But they want B to B in 2 weeks, right? So that means we want from here to here. Okay, so it could be like this also. I don't know whether there is a possibility or not. We have to check this also. There is a possibility. There is a possibility. Again, you go to from here to here, it will come. This time you are the winner. Next time you are not the winner. It will depend on the probability. Then you can come back here. So all these probabilities are there. That's why if you want to find B to B in 1 week, it's given. If you want to find B to B in 2 weeks, you have to find P square. And then you find B to B. Of course, if you find the whole matrix, not only you will get B to B, you will get B to A also, you will get B to C also. So this row is what we want. And you need to find P square. P square means matrix multiplication. You have already P. You multiply P with P. That is matrix multiplication. You will get these values. So let me write these values. I wrote here. See, P multiplied by P. We were interested in 0.31, 0.04. This is 0.31. This is 0.31. This is 0.31. Second row. This is 0.4029. We are interested in this row because the starting point is B already given. See, this is given. Okay, starting point is given. That is B. And starting with B now, what will happen after 2 weeks? This is the question. So to solve this question, you need to find all these values. Okay, because it talks about each member. Then this one, calculate the long-term proportion of each week's. Long-term means what will happen after 4 weeks, 1 week. So anyway, their transition matrix is there, right? 1 week probabilities. Now you found 2 weeks probabilities by just multiplying twice. That's all. Okay, I explained this one last time. How about 3 weeks? You multiply once again, 4 weeks, 5 weeks, 10 weeks, 15 weeks. You will get all. Now you have to find long-term probabilities. Okay, this is the question. Long-term proportion. This is what you need to find. For that, you need to find equilibrium. That is long-term proportion. Okay. Do I have any such answer? I don't know. Probably not. Okay. So you know how to find. For stationarity, you need to solve the equation. Okay. This. This equation you need to solve. 0.4, 0.3, 0.3, 0.3, 0.5, 0.2, 0.2. Now there is a question. Okay, we'll solve with the theorem. You solve this, find x, y, z. That's all, nothing more. Anything more? No, nothing more now, right? So let me go here. Here we have a very, very important theorem, okay, that I've written here. And we'll try to do this one today. Probably this is the statement of the theorem. See here, a Markov chain. We'll do one by one. I don't need any destruction here. Okay, no problem. Yes. This is the first one. A Markov chain with a finite state space. Finite state space. Markov chain with a finite state space has at least one stationary distribution. This is what it says. So you take any Markov chain. If it has a finite state space means whatever you have seen, 3 states, 4 states, 5 states. So we'll have infinite number of states also. States means you know what? This. Here we talked about 2 states. If you remember, 2 states. You can have 3, 5, 10, 15, 100, 200, 5,000, 10,000, 50,000. Finite number of states. Okay. Any Markov chain where your finite number of states will have at least one stationary distribution. Why they say this? At least means there will be a stationary distribution. That means there will be a position where if you reach that point, that is called convergence. After that, it will no more change. It will remain the same. Okay. I already discussed this concept earlier. If you have any doubt, you can go back and you can watch my previous videos. Here the theorem says at least one. At least one. What about the second one? Here comes the property irreducibility. What it says? An irreducible Markov chain. Here normal Markov chain. Here irreducible Markov chain with a finite state space. Okay, so this is there anyway. We are not talking about infinite state space here. So if it's finite and if it's irreducible, then unique. Unique means one and only one. Now I'll give you one example where you will have more than one stationary distribution. Now consider this one, irreducible aperiodic Markov chain. So two properties. Now irreducibility you have, aperiodicity you have. If both are present, and of course we are talking about finite state space only now, then that will settle down to its unique stationary distribution. Okay. So with questions, with examples, I will explain everything. So I think this is the most important portion of this topic. Okay, this will dominate 70% in terms of exam question also. Another 30% you have today I will discuss here. This theorem. This is 70%. I'll discuss first and then we'll go to the next one. How can you transfer my problem which is not Markov, but you will transfer in a way it will be Markov. Okay, we'll manage to make it a Markov chain by dividing one of the states. How that's possible? That's what we'll see. So let's start with this property, irreducibility. Okay, so let me draw one here. Now, suppose this is 1, and I can write 1 here, 1 here. Then let me write probabilities from here to here, here to here, and here to here. That is self loop. Or let me do this. Okay, no problem. Here to here, here to here, here to here, here to here, and here to here. So this is 1 by 3 probability. How about this? This is 1 by, this is trapped 1. Suppose this is trapped 1. So once you come here, you are trapped here in 2. You can never go back to 1. What about this? Once you come to 3, you are trapped here. You cannot go back to 1. However, from 1 to 1 there is a probability. From 1 to 2 there is a probability. From 1 to 3 there is a probability. So what will happen here? This is our diagram. So I can write something like this. 1, 2, these are the 3 states. 1, 2, 3, 1, 2, 3. Now what will happen in this case? Okay, this will become complicated. So let me not extend. So what it says, if it starts with whatever number, okay, suppose you start with 50, 50 or 100, 100, whatever, you take any number, okay. I'm not talking about the initial distribution. Let me take 100, 100, 100, doesn't matter. What will happen is, suppose 100 people are here, 100 people are here, 100 people are here. They are consuming 3 brands in a locality, okay. You can name them 1, 2, 3. Suppose 100 students, they are studying in school 1. This is school 2, school 3. Next year, they will change. What will happen? Those who are studying in school 1, they will change to another school, okay. The name, I mean, whatever is the name of the school, we number it 2. And some will also go 30% to 3. So I can make it 300 so that 1/3 I can keep. Nobody is saying you take equal amounts, but yeah, let me take, no problem. Suppose there are 900 students in that particular place. Okay, they are studying. Now see, we're trying to know the behavior. Okay, that's important. This is the locality and this is the school. 900 students they are studying. So what will happen is, after 1 year, what will happen? See, they are trapped. 2 and 3, they are trapped. They can't go anywhere. What will happen? Here 100 will stay, 300 to 100 next time. 100 will go here and 100 will go here, going by this transition matrix. You see 1, 2, 3, 1, 2, 3. So before applying any mathematical formula, you should know that 1 to 1 probability is 1 by 3, 1 to 2, 1 by 3, 1 to 3, 1 by 3. How about 2? 2 to 2 is 1, others are 0. 3 to 3 is 1, others are 0. So, let me confine this. This one. So here, let me write like this. and this is 1 by 3. Let me connect these two. So what will happen now? Here 1 by 3, 1 by 3. After next time period, what will happen now? Here you have 100. Here 400. I mean already here 400. Here 400. Okay. But here 100. Next time again, 1/3 will go here and here. So what will happen? A time will come when after a long time, here there will be no one. Because people will continue traveling to other states, and once they go to either state, they're trapped. Because this is the trapping one. They're trapped here. Okay, this is the logic you need to develop before uh, applying any mathematical formula. Now, you see what will happen in the long run if you want to know. Okay, so whatever proportion you start, I've taken equal amount 1 by 3, 1 by 3, 1 by 3. You can take 100, 100, 1000 also. It doesn't matter. You take because when we talk about stationary distribution, you start with 100 here, 100 here, 50,000 here. It doesn't matter. Initial distribution doesn't matter. Okay, don't think that always you have to take all. Now what will happen here, if you want to know the long term distribution, suppose we want to know the long term distribution. Now there is a question whether it has a solution or not. Are you sure you will always get a solution? Yes, you go by the theorem. This theorem says a Markov chain with a finite state space, because we are talking about finite state space only by now. So definitely they will have a stationary distribution, definitely. The only question is 1 or 2 or 3 or 4 or 5. At least one means one or more. Okay, so we have to see one example where there are more than one. We have to see example where there is only one. Okay, anything is possible. But when only one, if it's irreducible. Now, let's go here. The first one, if I remember, this is 1 by 3, I suppose. Yes, 1 by 3, 1 by 3, 1 by 3. And here to here, this is 1. Yes, you are trapped in 2 and you are trapped in 3. 0, 1, 0. Did I write here 0, 1, 0? Yes, this was wrong. 2 to 1, 1 I've written. Okay. So let me change this. Sorry. I think this one. You write here 0, 1. Trapped in 2, trapped in 3. So now if you solve this one, I mean the set of equations here, row column multiplication, you will get x by 3 in the left hand side, and in the right hand side we have x. Second equation will not take, I mean anyway you need to leave 1. Check the second one, no problem. X by 3 and here y. How about this? That is equal to y. The third one I am not taking. I will take x plus y plus z. That is 1. So you need to solve this equation. X by 3 is equal to x. How? That means here anyway we are getting x0. How about this? X0 means y is equal to y. Y is equal to y. So let me write y is equal to y. How about this? So x0, y plus z is equal to 1. That means x will be 0, y take anything. I mean this is not giving any value to me. Okay. So why this is happening, I'll tell you. Always you will not get the way you used to get when you solve equations in your standard 8th. Because what will happen is, see, even if I give to solve this one, x plus y is equal to 5. x minus y is equal to 1. It's good, right? 3, 2, x3, y2. If you add these two, you will get 5. If you subtract, you will get 1. So if the number of equations is equal to the number of unknowns, what will happen? You will have a unique solution, one and only one solution. How about this? Although I give two equations, but these are not two equations because they are linearly not independent. There is a dependency. If you multiply 2 here, you will get 10. So this is only one equation. So suppose you are given one equation and you are asked to find solution. You don't say that there is no solution. This is the equation of a straight line. There are infinite number of points. Here these are two straight lines. There is a point 3, 2 which lies on both the lines, this line and this line. That means this is common. This point is common to both. Okay, this point lies on this line, so that's where you get one line, one line. This is the point of intersection. How about this? There is only one line. There are infinite number of points, infinite number of solutions. So you don't say there is no solution. You say there are infinite number of solutions. It could be 4, 1, 5, 2, 3, 5 because you have only one equation. Here unique solution. Here more than one solution. You can write one solution, 1, 4, 5, 0. So many solutions are there. How about this? Because this is not contributing. Anyone can say y is equal to y. X0, we got it. Okay. But y plus z is equal to 1. That means you got one equation, whereas you have two variables. Okay. So definitely you will get infinite number of solutions here. Now we got x0. So we'll write, let me write once again because this is where all get trouble. And this is ours. So if I write solve these two, you write unique solution. If somebody will say solve these two, or maybe one equation, x plus y is equal to 10, you write k is a parameter, you write k 10 minus k. You take anything, x you take k here, so y will be equal to, you put x here, 10 minus k. And you say k is a parameter here, and if you change the parameter here, suppose you write k1, you have a solution 1, 9. You take k2, you will have a solution 2, 2, 8. 2 plus 8 is 10. See, ultimately, if the equation is satisfied, then this will be a solution, right? Then you take k 2, 3, 5 minus whatever you want. You take 0 also. I'm taking 5. This is 5, 5, 5, 5 is a solution. So infinite number of solutions here. How about this? We got already x0. So let me write x, y, z. X is already 0. We have. How about y? Y. And how about z? What is y here? Y is y. You can take k here. And you can use this equation. Y plus z is 1. So I've taken k here. So 1 minus k. So these are the solutions you will get. You can say that it is no solution. You see what it says. Finite state space, if it's irreducible, has a unique stationary distribution, one and only one. That's unique. Okay. So unique when we say one and only one. But here, it's if it's irreducible, then only this is guaranteed. But in this question, that's irreducible or not, we'll check later. But in this question, you see how many solutions you have. 0. You take K1 first. 0, 1, 0 is a solution. You take K2, 0, 2. I mean, it will be negative. Of course, we will not take it. Is the total 1 here? Yes, total is 1. Total probability must be equal to 1 here. So Anyway, it's 1 minus k, it can't be. So you do one thing. You write 1 by 2, this will be 1 by 2. You write 1 by 3, this will be 2 by 3. You take 1 by 8, this will be 7 by 8. So this means what? This means what? This means logically, if you are really developing the topic, see what's happening. See this graph, okay? Again, I am writing here. Let me use this. In the long run means after many years, if you are considering yearly, or you can say time periods, 1, 2, 3, 4. So what will happen after hundreds of years, okay, or hundreds of minutes? If it's, I mean, the time the gap is 1 minute, okay, 100, 101. You write like this. We don't know, okay. We are not considering this. So what we are saying is, we started with this here, okay. Many are studying here, many are studying here. What will happen, because once they come to 2 and 3, they are trapped, okay. So ultimately what will happen, there will be no one here. So only you see students here and students here. How they are distributed here? What will happen is, you see, they will be converged in many ways. Many ways means half up. Half up means what will happen is, when they are equal, suppose they, once they are equal, now there will be no more change. They will be equal only. This is one way. I mean, we don't know whether the stationarity will be reached this way, equal way, or unequal way also. Unequal in the sense 1 by 3. I mean, here though it will be 0. No one is here. Okay, this is empty, totally empty. First one is empty. That's already confirmed. What about second and third? It's not that they will be equal. What will happen is, if you reach 1 by 2, 3, 2 by 3, then also it will stay that way only. That means, suppose we started with 300. If you remember, we started with 300, 300, 300, total 900. Okay. So by chance, if you reach at 450 here, 450 here, they're equal, that will continue. That's what it says, half up. The total 900 here, there will be no one studying. Okay. Suppose we are talking about 1 day. Okay. Because that time 100 years will not come, whatever, like this is time period. Okay. Or you can say there are 3 classrooms, they are sitting in each classroom each day, whatever way you define. After a long time period, what will happen, there will be no one here. The people will be here and here, but not in the same proportion. This is one of the solution. There is a solution this also, 1 by 3, 2 by 3. That means total, I mean, total if you divide into 3 parts, total is 900, 3 parts 300. So it could be like this also. Okay, it could be like this also. Let me erase. Instead of this, it could be this also. This means here, the second one, 1 by 3, and this is 2 by 3. 1 by 3 means 300, 600. Then also it will not change. It will continue to stay after this time 300, 600. This is what it's saying. Stationary means what? It will no more change. If it reaches this proportion, that means stationary already reached. After that, it's not going to change anymore. Even if it will reach 1878, then also it will not change. Can you prove this? Yes, we can prove it. We'll check. We'll multiply here. We'll multiply because we solved this equation. It's not by chance we solve this equation. So you put 1 by 1 and you check. You will get the answer. Suppose I'll take the second one, 0, 1 by 3, 2 by 3 multiply. 100% you will get 0, 1 by 3, 2 by 3. That's what it says. Infinite number of solution means what? This is a solution. This is also a solution, 0, 1 by 2, 1 by 2. This is also a solution. You try with this also. But let me try with these two. 0, 1 by 2, 1 by 2. 0, 1 by 2, 1 by 2. You will get it for sure. 1 by 3, 1 by 3, 1 by 3. 0, 1, 0, 0, 0, 1. What about this? 1 by 3, 1 by 3, 1 by 3, 0, 1, 0, 0, 0, 1. Matrix multiplication. Okay, 0 multiplied by 1 by 3, 0. 1 by 2 multiplied by 0, 0. 1 by 2, 0. So first one is 0. How about the second one? 0 multiplied by 1 by 3, 0. 1 by 2 multiplied by 1, that is half. Half multiplied by 0, that is half. I got it. Of course, you will get it. Total is 1. How about this? Again, 0. First one I got it. Second one you see 0 multiplied by 1 by 3. 0. 1 by 3 multiplied by 1. That's 1 by 3. Then 1 by 1, 2 by 3 multiplied by 0. That is 1 by 3. Okay. And I got this. So this is stationary. This is stationary. So in many ways it becomes stationary. So this is called many solution. What about this? What it says? This says actually unique. Unique means one and only one stationary solution. Unique, that is unique. But here, at least one it's saying. It's not saying if you solve, you will get one only. At least one means one or many. So we got many here. Doesn't matter. So when you will have unique, if it's irreducible, that is what it says. The theorem says irreducible means one and only one. Okay. But if it's not reducible, then you can say that it is many. That it doesn't say. See, theorem is very important. Theorem means what? Theorem means only one way it says. Two way is not there. It implies what it says. If three sides of a triangle are given, you can construct a triangle, right? If three sides are given, then you can construct a triangle, right? You know, 7th or 8th standard. So we never say if three sides are not given, you can't construct a triangle. I mean, it never say that, right? It says if three are given, you can construct a triangle. That's all we'll use. If three are not given, suppose two are given, one angle between these two are given, then also you can construct a triangle. Okay. So forget about this result. You concentrate on this result. This result says three are given, you can construct a triangle. If three are not given, I mean, we are not saying anything. So that means here you have to take it carefully. If it's irreducible, because I will show you two problems from the material. I mean, there is a lot of confusion. Students ask me many times, if it's irreducible, then it will have a unique stationary solution. That's for sure. It's guaranteed. Theorem guarantees this one. However, if it's not irreducible, means it's reducible, then you can have, I mean, we are not saying anything. Okay. The theorem says only this. If this will happen, this will happen. What is irreducible? We'll check now. Now check whether this is irreducible or not. Go here. So what we are saying is, can you go from each state to any other state? Suppose you start with 0, first state. Can you go to 2? Yes, there is a way. Can you go to 3? Yes, there is a way. There is a probability. From 3, can you come to 1? No, you can't come. You are trapped here. That means what? Irreducible means there is a way from each state to any other state. There is no way here. So this is not irreducible. Let me write here. Not irreducible. Okay, not irreducible. That means reducible. So if reducibility is there, we will not apply this theorem. See, this theorem is not about reducibility. It's about irreducibility. If it's irreducible, then unique. Because it's not irreducible, that's reducible, then I mean, we got many. Sometimes you get 1, 2, 3. Unique also, many also. I mean, in this example, we have many. Maybe in another example, you will have unique also. Will not worry because that result is not given at all. Why to worry about something which is not given? What is given? We'll think about that. Given, if it's irreducible, we have problems. Okay. Then you check that there is only unique. For example, there are so many. Whatever I discussed till today, all will fall here. Irreducible only. Whatever examples I must have given by now in the last two classes today also, all are irreducible. And they have a unique. We checked it. I'll give you another here. I'll give you another here because from here we'll go ahead. Suppose you consider this one. Let me delete everything. It's running, right? Yep, no problem. Now we'll go here. Okay, this example. I'll write 1, 2 here, 1, 2 here, half, half of total is 1. If you see this one, this is like this 1, 2, here this is half, here this is half, here this is half, here this is half. So that means 50% will stay here, 50% move from 1 to 2, from 2 again 50% they will come to 1. So if you solve this, okay, if you solve this, you can write half here. If you solve this one, what will happen? X by 2 plus y by 2 is x. Okay, that means the first equation will be x by 2 plus y by 2, that is x. So x is equal to y. This will give you the first equation. X is equal to y. Okay, I'm not writing the second equation. X plus y is equal to 1. So I'll these two. Then I will get x half, y half. That means I have a unique solution. Okay, now if you check this one, this is irreducible. Let me write here, irreducible. Why this is irreducible? If you start from state 2, if you start from here, you can go here, there is a probability. If you start from here, you can go here, there is a way, there is a path, there is a probability, there is a chance you can go. So every state here, from every state, you can go to every other state. Okay, so again, I am only discussing whatever is required for actual science career. Okay, we're much more than this, and there is a theoretical derivation also. I'm not going to that. Okay, now this is irreducible. Now we apply the theorem. If you go to the result here, if it's irreducible, you check that unique. Yes, irreducible, unique, done. The previous example that was reducible. So we didn't, I mean, we never required to verify the result because the result, the theorem says about irreducibility. That's all, done. Now we'll go to this example, aperiodic example. Now this is one example. Let me write here example 1. Now let me write another one, example 2. Here what will happen? Here I have similar two states only, 1, 2. 1 always goes to 2. 2 always comes to 1. I mean, nobody stays here. There is no self loop here. Acha, I have to write 100% probability, right? So let me erase this. This is 100%. So if you write the transition matrix, it will look like this. Here, 1, 2, 1, 2, and there is a probability 1 to 2, 1 to 1 0, 1 to 2 100%, 2 to 1, 2 to 1 yes, 2 to 1 we have 1, 2 to 2 0. Okay, now find stationary distribution. You have to find stationary distribution. To find stationary distribution, you multiply this one with 0 1 1 0 and you get xy here. If you see here, x multiplied by 0, that is 0, y multiplied by 1, that is 1, that is y, is equal to x here. The next equation, x will be equal to y. And of course, we have another one. You have to solve these three. So if you solve these three, x will be half, y will be half. That means we have a stationary distribution. We have, okay, see, why I said today's class is very important. If you are here now, or you will come later someday, you will watch here. This is where more than 90% of my students, they definitely struggle. Okay, I'll spend 10 minutes here. See this result and see this result. Okay, these are the two examples. Example one here, same I have half up. What about example this? Here also up, here also up. Okay, let me erase this and write within the box. Here half up, here half up. Okay, so I'll discuss both. Remember this. Okay, let me write here. This one, this is the example. 100% probably they are moving. What about this? This is the example. Okay, this is the example. This is irreducible because from every state you can go to every other state. There is no problem. But that is not sufficient. That example is not sufficient. That is what? That's why we have another one property. Let me write here this way. Done. Now I'll go here. Let me divide this. I think I can. Oh no. Okay. Let me copy all and paste here. Now time period. Here also. These are the two stochastic process and Markov chain. Now, suppose let me write 1, 2 here and we'll also write the probabilities. 1, 2, 1, 2, 1, 2 here. Here also 1, 2, 1, 2, 1, 2, 1, 2. If you remember the example, this example was this, the left side. One, two, there was a probability also, that is 0.5 half up and self loop also 0.5, 0.5. How about this? 1, 2, 100%, 100%. There is no self loop. Now, mathematically, if you start with suppose 1 and 2, these are the two positions. Suppose these are the two, you can say, two hospitals. In the locality 1 and 2. Suppose 600 they are treated here and 400 here. 600 here, 400 here. So what is the initial distribution here? I mean, if I if this is my time 1, time 2, time 3, time 4, time 1, time 2, time 3, time 4. So my initial distribution at time 1, that is probability of x1 is equal to 1, that is equal to zero point 0.6, that is 6 out of 1000, 60%. Probability that x1 is equal to 2, that is 0.4. This is my initial distribution. Okay, initial means when we started observing, we saw that 600 are getting treated here, 400 are getting treated here. Okay, that's what we have. Now we'll see what will happen after a long term starting from now. So if you go through this one, already we have. So if you see the solution here, half up, half up means 50-50. So what will happen ultimately? They will become 500-500. Okay, this probability ultimately, suppose you see after many times, we can check what will happen here. 50% will go here, 50% will go here. That means this 50% will go here. 300 will stay here, 100 will come from here. Sorry, 50% will come here, that is 200, and here from 600 to 50%, that is 300. Here you will get 50%, that is 200. So 500 we are getting here. 500 we are getting here. Now that is 50-50. So here in my case, x2 is 0.5. This is the exact number, absolute number. This is the probability. 2 is 0.5. So what's happening here? So now you have 0.5, 0.5. So once you reach this number, what is stationary? Stationary means once you reach this level, this state, this position, half up, it will never change. You check it now. It will no more change. I mean, you can say you are very, very, I mean, fortunate that you get your stationarity after one step. I mean, if you change the stationary, I mean, this proportion, maybe you will not get. That's a separate thing. I'm not going to that. But here in this example, you already got your stationarity. Okay, let me take another one. You got here your stationarity. Okay, you already achieved 0.5, 0.5. So that means it will no more change. You check it. 50% of 200, 500 is 250. Here 50% they will come. That is another 250. So 250, 250 combine, you will have 500 once again here. So total 500, again here 500. So no, I'm not writing. So that will no more change. 500, 500 will no more change. Okay. That is your stationarity. That means you say that fortunately, after one step, I got my stationarity, and stationarity, according to the definition, it's like this only. It's never gonna change. It's never going to change. So I will get 500 after, I mean, starting from here forever, you can say this will remain in this state only. Now, see, what is that I said? Now, there is no guarantee that it will reach here. That is what we want to see. Here it reached. How about this? Let's check here. Okay. So according to this, all the people they are getting treated here, they're taking the treatment from hospital 1. Next time, they all will go here. 600. I mean, going by the probability, all will go. I mean, due to whatever reason they didn't like. Hospital 2 is also in the similar situation. The people, I mean, due to whatever facility they have, they didn't like either. They all will come here. They want to see whether this hospital is better than the other. They want to check here. So all 400 will come here. Mathematical also you can do. You start with this. Probability x1 is equal to 1.6. Probability x1 is equal to 2.4 here also. But how about this? Probability of x2, here this is 0.2, is equal to 1. Probability of x2 is equal to 2. This will be 0.4, 0.6. Mathematical also if you do, you start with 0.6, 0.4, you multiply this matrix 0, 1, and 1 0. This, if you multiply, what will happen? 0 0.6, 0 0.4. This is 0 0.4, 0 0.6. So that's where you got 0 0.4, 0 0.6, 400, 600. Next time it will go here. Next time you multiply again, you will get 400 here, 600 here. That will continue. After one time period, two time period, 3, 30, 40, 300, 3,000, 3 lakh, 3 crore. That means when you will reach stationarity, you will never reach. But mathematically we proved. Mathematically what we proved? Half up. We proved it here. You see, we proved that stationarity is half up. That means we proved that what? If you take wrongly, that half up will be reached. No. Stationarity never say that. Stationarity says if you reach this level, then it will never change. But whether it will reach this level or not, that's a separate question. See, we're not reaching here. We're not mathematically we prove that. This means what? This means actually here also. This means if I write half up here, here I will write half. Mathematically, I'm saying. Practically, if you reach here, if you are here, how you are here? We are not saying. If you are here, this is called convergence here. Then mathematically multiply, you will get half up. This is true. This is true. Even here also, somehow I'm saying it will never happen. That's a separate thing. Somehow, if you reach 500, 500, if you reach, then to stationarity, I mean, there is no problem. This 500 will go here. This 500 will come here. No problem. There is no change. So it will continue. That's what it says. What it says, stationarity says, if you reach here, then it will not change anymore throughout life forever. So if you reach here forever, but you are not reaching here, but you are not reaching here at all. You are not reaching here at all. That is the problem. Because if you start with 600, 400, all will go here, all will come here. Again, they will interchange. That way only it will continue. It will never come to this level unless you start with 500, 500. That's the problem. So there is no one. There are two properties actually. One is having stationarity. The second one is converging to its stationary distribution. Okay, I can give one example here to differentiate. So there where I will introduce periodicity, aperiodic concept. Okay, then we'll complete that theorem. That is part 1, 70% of today's class. I will be completing in another 10 minutes. So let me write here. So what I'm saying here, let me check if draw something here. Suppose this is my house. And I want to go to airport. Okay, here. This is my house, and I need to go to airport here. That is here. That is here. Okay. I want to go here. This is airport. And this is my house. I want to go from here to here. So now somebody said me this 20 kilometers. Okay. So there is absolute no problem. You can go easily and you can reach here. The only problem is whether you will be able to reach here or not. Okay, if you are able to reach here, because there is a lot of traffic here and there is some function going on, and this is the only way you can go from here to here. Once you reach here, then you will be able to reach here for sure. But you will reach here or not, today I'm not sure. So you see what you can do, whether you can cancel your ticket or you take a chance. Okay. So that's what this guy says to me. Okay. I'm on a bike. So reaching here is one thing. Okay. And then going here is another thing. Reaching airport is another thing, right? So if you reach here, there is a guarantee. Okay. But if you don't reach here, I mean, there is no question. We will not discuss about this. That's what it says. What it says? So suppose you have a Markov chain, here, and 2, 3, 4, 5, whatever number of states you have, it doesn't matter. You have a stationary distribution. Stationary means the probability will no more change after some state. Suppose you reach stationarity here, whatever level, like suppose 0.3, 0.6.1. This level, so starting could be say 0.9, 0.01, 0.09, total is 1. So this is initial distribution, and this is the distribution where you reach the stationary distribution. If you reach here, then it will not change for sure. Okay, this is called stationarity. Stationarity means what? Here the probabilities are changing. 0.9 to suppose you might get 0.7, you might get 0.1, 0.1 after one time period, after two time period also, the probabilities will change. That way, they will change. But a time will come when there will be no more change. That is stationarity. So stationarity means what? It's not changing. Okay. All right. Also, I've taken unique 16.3 only. One way it's not changing. But even if it has mathematically proved, there is no guarantee that here you will reach. Okay, that's called convergence. Okay. So this is called converging to its stationary distribution. Having, achieving, they're different. Okay. Having the potential, achieving the potential, they're different. Now, that is the last part of the theorem. What it says, we'll do that. This is the last one. See, it says an irreducible aperiodic Markov chain. Finite, so we are taking anyway. Finite we are taking anyway. We never discussed till now. This is the third class. Infinite state stochastic processes. I mean Markov chains. Okay, we have never taken. What about this irreducible? I discussed already. Now I will discuss aperiodic. If it's aperiodic and irreducible, if both are there, then what will happen? The Markov chain with a finite state space will not only have its unique station and distribution in the long run, but also it will settle down, means it will converge. You can write converge also. Settle down means it will reach, it will converge to its station and distribution. That's what it says. Okay. So we'll now discuss aperiodic property. So what is aperiodic? You go back to this question here. Let me write both the examples. Now, what is aperiodic? Aperiodic. Remember our example? Let me divide again into two parts. So, if you remember, very sad. I wanted to keep at 60. Okay, 60, 70. So now let me divide here and write 2 here, 2 here. Now, this is 1, this is 2, this is 1, this is 2. There is 100% probability. There is 100%. There is 100% probability in this case. You can take any other example. This is the exist example. I remember this is 0.5, 0.5, 0.5, 0.5. There is self loop here. Now I will find period of the state 1. And period is a concept here. It's a state concept, not a Markov chain concept. What is the period of the whole stochastic process of Markov chain? If they're equal, that common one. Now, period of one you find GCD, you can write GCD, greatest common divisor, or you can write HCF also, highest common multiple, whatever, HCM. So GCD of once it leaves state 1, where it goes? Suppose it leaves, it will go to 2. In how many steps? 1, again 2 to 1, 1. So once it leaves, in how many steps it come back once it leaves. So we'll do this one also. Let me write period of 1, period of state 1, period of state 2. What is period of state 1? You can write HCF or GCD, whatever you write. If you leave 1, in how many states you will come back to 1? Okay, 2 times. You go here, then come back here 2. Then once again you go, come, okay, 4, 6, 8. So highest common factor is 2. 2 also, you leave 2, you go to 1, come back. So 2, in 2 steps you can do, 4 steps you can do, come back. Okay. So this is like, what is period? Once you leave the state, okay, the nodes anyway you will get it. Okay, we are not spending time because we will focus more about time solving exam questions after developing concepts, right? So what is period of 2? Once you leave 2, once you leave 2, then in how many steps you will come back to 2? Okay, 2 times, 4 times, 6 times, 8 times again. So 2, they are matching. So the period is here, they are matching. So period of whole Markov chain is also 2 because all states have the same period. So now it has period 2, so it's periodic. Periodic when we say, when period is greater than 1. Here period is 2. Okay, so it's periodic because it's greater than 1. So this one is, let me write periodic. Remember, we are not interested in periodic, we are interested in aperiodic. Aperiodic, okay. Here this is aperiodic. Why aperiodic? Because once it will leave 1, it will go here, it will come back here. The 2 is already there, 4 is already there, 6 is already there. In addition to 2, once it leaves 1, there is a 1 also here. There is a 3 also. How 3 is possible? 1, 2, then self loop 3. Or start with self loop 1. So 1, 3, 1. Acha, 1, sorry, 1, because if it comes 1, you can take this one again. 1 here, there is a loop here, it can come. That way it could be 3. 2 possible? Go here, come here. 2 possible. 1 possible? Yes, 1 possible. So 1, 2, 3 for all that. Here also 1, 2, 3 for all that. So you are getting 1 here. 1 here. 1 means what? This is aperiodic because period is equal to, because P is 1 here. P should be here, P is greater than 1. So P is 1 means it's aperiodic. Periodic means what? Like sine x, cosine x. They repeat after one time. That is called period. If something is repeating after a certain period of time, that's periodic. It's not periodic because it's 1 year. So if it's aperiodic, then it will converge. It's periodic, it didn't converge, you see, because it's revolving here and there. I mean that I lost somewhere. Anyway, this is aperiodic. This one is aperiodic. So if you go back to that example what we did, see this one, last one. Aperiodic, irreducible, and aperiodic Markov chain with a finite state space all satisfied. So what happened is it converged, it settled down to its unique stationary distribution. Not only it started, but it was able to reach. Remember that example? Let me go to 10% level. Yeah, I will get now. Yes. If you remember here, this one. So here, in this example, see, this 600, 400, 400, see, we continue this way, right? We were never able to reach the stationarity 500, 500 here because this is periodic. But here we are able to reach because this is aperiodic. That is the only reason, okay? 0.5, 0.5 probability and absolute number 500, 500. We are able to reach. Here we were unable to reach, okay? And you will see In material, we have also 3-4 more examples. You can go through that. So this part is over at least. Okay. So one part of today's is already over. Now we'll go to next part, the other part. For that, I wrote a problem here. This is no more required. Now we'll go to this part. I don't think I will be able to complete today. I need, because the classes will be 2 hours, probably I will take another 0, 1, 2. I mean, this was earlier. Now 0, 1, 2, 3, 0, 25, 40, 60. Okay, let me write here. Now I'll discuss another NCD, no claim discount. NCD, no claim discount. Here we have 1, 2, 3, 4. And in terms of stochastic process, I have to draw this way. 1, 2, 3, 4. And not only this, I need to copy this. No. After 1 time period, after 2 time period, after 3 time period, 4 time period, 5 time period, 6 time period, 7 time period, 8 time period, 9 time period, 10 time period, this. This is stochastic process. And we are observing change, whatever way the definition was. This is 1 time, the starting time you can say. Then time 2, time 3, time 4, 5, 6, 7. No claim discount system. General insurance. This is general insurance concept. So what will happen? There are 4 states here. There are 4 states here. The states are 0% discount. You see here 0%, 25%, 40%, 60%. 0% discount. This is state 1, you can say. This is 0% discount, 0% discount, no discount. And this is 25% discount. I think 40, 60. Yes. 40% discount, 60% discount. That means, suppose I'll purchase a car here, and of course, I will not get any discount now. I will have to pay 10,000 premium, 0% discount. I have to pay everything here. I'm here. I'm rated. Okay. This is part of experience rating. I'm here now. I'm here. I paid 10,000. Next time, if I don't claim, I will get a promotion. I will get 25% discount. 25% means I will pay 7,500. If I will not claim during another year, okay, then I will get another promotion. If I will claim, then I will go somewhere down once or twice. This is a problem. There is a, demotion, 2 demotion also. So if I will not claim, then I will again go to the top. That way, I will go on increasing. See, up to 60% discount I will get at most. 60% I will get. This is one scenario. It could be like this also. Here, then here, then here, then here. It could be anything. I took one scenario. So what it says, it says maximum 60% discount. That means what will happen? I will give only 4,000. Initially, if I pay 10,000, I will end up paying 4,000. And if I will not claim, I will continue to pay 4,000 to the insurance company with 60% discount. However, if I claim, if I will not claim, what is not claiming probability? Claiming probability. Let me write. This is no more required now. What is my claiming probability? Whether I will claim or not. How you get these probabilities? Of course, here this is a problem given. Otherwise, you have to check a past sample and you will get these probabilities. Okay. 0 to 0 also there is a probability. 25 to 25, whatever, we'll check. Now, what it says, rules are moving up the discount scale remain the same. That means up is already, I think, 75%. Yeah, no claim means moves up. Claim means one down. Okay. Second one is same, but here there is another condition. Okay, we'll see this one. This is extra. This one we already I discussed in the last class. Okay, this is not new one. The second one is new here. Okay, and now see, I will tell you the problem. It says if you will not claim during a year, you will get one promotion. That's fine. And getting a promotion probability is 25%, and not getting promotion is 25%. Total is 1. Now someone uh, is now at 25%. Again, there is a 75% probability that he will uh, not claim during the year, he will get a promotion. 75% probability that he will not claim during the year, he will get a promotion. So the same thing remains, they say. Not claim, again, not claim, 75% not claiming. Okay. So not claiming means 75%. How about claiming here? Okay. Claiming here. So I think I need to delete this symbol here. Now not claiming. These are not claiming. What about claim? If you claim, what will happen? If you claim at some level, now see what they say. The not claiming was 25% before. Okay, before it was 0.25. Not claiming 0.25, not claiming 0.25, something like this. But now not claiming means at 25% you will claim. You will not claim means you will get a promotion. If you claim means there is a 25% chance you will come one down. Here come one down, here come one down. That's all. Now, this is the problem we already uh, we studied. Now, this is another problem. Here, if you will not claim, though you get promotion, the probability is 75%. If you claim, what will happen? They say, if you claim here, now see, moving up probability 75% and same. Moving down here, they say, you are one step if previous year was claim free. Two steps if previous year was not claim free. Not claim free, then one step. Okay. Claim free means if your past record is good, previous year was claim free. I think there is a mistake in the question itself. One step they will down you if the previous year was claim free. I don't think this is correct. Two steps if the previous year was not claim free. That means your past is bad, so they will take down two steps. It's like this. It's like this. Suppose you are here. Suppose you are here. I'll consider these two time steps. Okay, these two. I'm interested here. Now, what they're saying? They're saying if you are here, then we'll take you two step down. We'll take you two step down. When? Under what condition? If your past is not good. Okay. So I don't know how staying at 60% your past is not good. Because how you are here. How you are here. Either you came from here, you got a promotion, you are a principal now, or you were the principal before. Okay. So there is no chance that, you got a demotion and you came here. There is no way. You are not the director, you are not the owner, you are the principal, right? That is the highest position. Now you are at a highest position means, of course, your past is good. Either you are a principal or you got a promotion to the principal, right? That is the highest position. So, I mean, that means your past is good. So, if someone claims here at highest level then they are saying they will down here. I mean, next time here. That's very clear, no doubt. Okay. How about this? How about this? Let me delete this too. How about this position? You are now you are now here. Suppose you are here at this level, 40% discount level. Okay, let me not use the discount levels. Better, I will use 1, 2, 3, 4. This is 1, 2, 3, 4. You are here 3. You are at 3. Now you are here means what? How you are here? Either your past is not good, you got already a demotion, you met with an accident last year, you claimed and you took some benefit. That means your past is not good. You met with an accident already. Or you got a promotion as well, because you can be here from here also. That you have to check. If you are from here, that means your past is good. If you are from here, your past is not good. Then what will happen? If you will not claim here, that's fine. You get a promotion. I mean, your past is not important. If you are not claiming, you get a promotion for sure. Even it applies in healthcare also. Because we claimed once, there was a serious problem. So what happened? They didn't give any discount. Anyway, however, if you claim here and unfortunately your past is not good, then they will take you here directly from 3 to 1. That's what they're saying. They will take from 3 to 1. If your past is not good, that means you claimed once, your past is not good. You are at 3, your past is not good. So they will take here. However, you got a promotion, then you claim here, that means your past is good, then they will take you one step down here instead of here. That's what they are saying. Instead of here, they will take here. In this case, they will take here one step down. They will take you to 2, not 1. They will take you to 2. If you got a promotion and you reached here now, then they will take 1 level down. Otherwise, they will take 2 level down. The problem here is from 4th, there is no problem. What about this? Here, if you make a claim, it's like suppose you killed someone. You killed 1%, 2%, 100%. It doesn't matter. You get a Fase means what? Hanging, like they will hang you. Okay. So, I mean, even if your past is not good here, how it will matter? Because they can't, there is no such -1 step here. So, -2 to 1, you will go for sure. What about here? You make a claim. You will stay in the same position. What about you claim here? They will take down one step only, because you are here means your past is good. Either you got a promotion or you were here. Your past is good. Your past is not bad. Only at 3 there is a problem. Now, if you try to draw the diagram also, Markov chain, sorry. Now let me try to draw the diagram of Markov chain. How I will draw? You don't claim, you get a promotion. Awesome. Done. This is 1, 2, 3, 4. And you claim here, you got a demotion. One demotion only, because there is no -1. Here you make a claim, you'll go to 3. That's fine, because you are at 4 means your past is good. And you didn't claim means you will be the principal. You will continue to stay here at the highest level. How about this? You will not claim, you come here. How about this? You will not claim, you come here. Okay, everything is over. At 2 also, see, your 25% probability, 75% probability, total is 1. At 1, 75% probability, here 25%. That's done. At 4 also, 25%, 75% that you will not claim you will be the principal. Otherwise, you will come down to the vice principal level. Okay, if you do some mistake, whatever, I mean, way. So what will happen is in this case, the probability is 25% they've given. It's also done. The problem only comes here. Okay, at 4, probability is 1. At 3 also, this one, yeah, we don't know this. At 2 also probability 1, 1 probability 1. What about 3? 3, because either they will down you here or they will down you here, depending on whether your past was good or bad. So that means if you go by the definition of Markov property says you depend only on present. You depend, or you can say, if you want to know about today, you see what happened yesterday, not before, not day before yesterday. One step dependency, one step. You can go back to 2 steps. Now we are taking 2 steps here, right? We are not only taking the present to forecast future. We are taking whether my past is good or not. I'm going to past. That's a problem. It's not Markov. Even you can draw a graph like this. Okay. If it's Markov, then only you can draw a graph like this, because I mean, whether you like this one or this one, you don't know. It depends on past. So this is not Markov. So now the question says you change it to a Markov one. You change it to Markov. How will change it to Markov? We'll do this. I mean, there is a problem here only. So we'll target this one. We'll target this one. We'll make it 2 states. Now, let me not worry about this. We'll make it 2. We'll name one 3 minus 3 plus. Okay, whatever way it is. Do we have something like that? Okay, nothing in the question. So will not worry. I mean, you are free to write anything 3 minus 3 plus. You might get a different one also if you do from the material. 3 minus, suppose this is 3 minus. Let me check. Okay, whether it's 3 minus or 3 plus. I mean, this theorem over. I think this is over. Whatever way it's defined, we'll do that way so that you will study the same thing. There won't be any doubt. Where am I? No, this is chapter 4. Yes, this is convergence, so I have to go here. This is a very, very important problem. This is an exam question. Yeah, something left. Acha, 2 plus 2 minus they've written. Okay, what is 2 plus they defined? Let me check here. 40% discount, no claim in the previous year. Okay. 40% discount and no claim in the previous year. No claim means claim free. Okay. 2 plus. This is claim free. Okay. 3 plus is claim free and 3 minus is claim. This way. That means it's like this. We have divided into 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. In this example, suppose, so how you are at 3 plus? I mean 3 with a cap where plus is written. Okay. Uh, you have a cap. Okay. Green cap. You have a plus. That means last year was claim free. That means how you came from last year? This diagram is equivalent to 2, I can write, oh, sorry, this is 2. No, this is 2. 1, 2, 3, no, yes, 3 plus 3 minus 4. So 1, 2, 3 plus 3 minus 4. So you are at 3 plus here. That means you must have come from here because you got a promotion. You come to 3 plus. That way you are here. Okay. At 3 plus, if you make a claim, they will make you down one step. 3 minus means your past is bad. That means you must have, uh, I mean, made a claim last year. You met with an accident last year. That way you are here. Okay. And what about 3 minus 1? Here they will take you 2 step down. 3 to directly 1. Here they will take 1 step down because your past is good. Okay. And here 4 if you, 4 over. 3 plus if you will not claim means you will go here for sure. You will not claim here means you will go promotion. But if you claim here, you will go 2 step down. If you claim here, you will go 2 step, 1 step down. That is the only difference. Okay, so we divided like this. So what happened is here my past is already there. So what we did is there were 4, we divided into 5. Then this became my Markov chain. Okay, this is my this satisfies Markov property. The earlier one with 4 states, it didn't satisfy my Markov property. So what we did is, I mean, this past we clubbed into this one only. The information is contained here in my cap. It's written, so someone can see me and say whether they will down me 1 or 2. That way, it became Markov. So all this now you write in the form of a matrix, then you do it. So yes, still I have something. See what is left. We have Poisson process. This is very, very important in terms of concept also, because you will be working in company. Random walk, if you've studied CM2, that's fine. Otherwise, random walk, that will come again in CM2. So random walk, Poisson process, also Poisson process will come in the next topic. So we have a chance to discuss once again. There are 4 ways we can define a Poisson process. This is so important. Poisson process, again, a bit was there in CS1 also, but I don't know how you must have studied. That we'll do next time. Poisson process, random walk, and some problems we'll do. Probably it will take 40 minutes. Then we'll go back to the next one. Okay. For today, the class is over. See you next time. But before that, I'll check once if someone is there. No? That's fine. All right then.